Welcome to the first lesson on linear regression. In this topic, we're introduced to a model built around two variables, an independent variable and a dependent variable. Our goal is to understand how a linear regression model describes the relationship between them and how we can estimate and apply the parameters of that relationship. Let's begin with something relatable. Imagine you want to predict how well you might perform on your CFA exam. One way to approach this is to look at past students' results and see whether there is a pattern between their exam scores and the number of hours they studied. Here we have two variables. The dependent variable, which we'll call y, is the outcome we're trying to explain in this case, the CFA exam score. The independent variable, x, is the factor we think helps explain that outcome, the number of study hours. To get a feel for the relationship, we can start by plotting past observations on a scatter diagram with study hours on the horizontal axis and exam scores on the vertical. When we look at the pattern of points, we can often get a visual sense of whether a relationship exists. If the points tend to move upward together in a roughly straight pattern, that suggests a positive linear relationship. When the relationship is linear and we have just one independent variable, we use what's called a simple linear regression. The model is written as y equals beta, 0 plus beta, 1 times x plus error term. Here, beta 0 is the intercept, beta 1 is the slope coefficient, and epsilon is the error term, capturing the part of y the model doesn't explain. Before we estimate this line, we need to understand the assumptions that make the model valid. The first and most intuitive is that the relationship between x and y is linear. If the true relationship curves or bends, a straight line won't capture it well. The remaining assumptions concern the error term. The independent variable should not be correlated with the errors. As x increases, the residuals shouldn't drift upward or downward in a pattern. The average value of the error term should be 0. The variance of the error term should be constant, a property called homoscedasticity. Errors should be independent across observations. In other words, the error for one student should not predict the error for another, and finally, the errors should be normally distributed. With these assumptions in place, regression analysis chooses the line that best fits the data by minimizing the sum of squared errors, the total squared distance between each actual exam score and the score predicted by the line. This is known as the least squares method. To estimate the line, we need to compute the slope coefficient beta 1, which is the covariance of x and y divided by the variance of x. You're not expected to derive this formula under exam conditions, but it's useful to know what it represents. The slope describes how much exam score is expected to change for a 1-unit change in study hours. So let's work through a small example. Imagine we have 11 observations showing the number of study hours and the corresponding exam scores. After calculating the variance of x and the covariance of x and y, we find a slope. Coefficient of 0.23. What does that mean? A slope of 0.23 suggests that for every additional hour studied, a student's CFA exam score is expected to increase by 0.23 points. Next, we estimate the intercept, beta 0. Using the sample means of x and y, suppose we find an intercept of 25. The intercept represents the predicted exam score when study hours are 0. In our example, it suggests that even without studying, a student might earn around 25 points, not particularly meaningful on its own, but mathematically necessary to anchor the line. Putting both parameters together gives us the estimated regression line, y equals 25 plus 0.23 times Tx. Now we can make predictions. If a student studies 200 hours, the model forecasts an exam score of 25 plus 0.23 times 200 equals 71. This gives us a structured way to link study time with expected performance. Let's do some practice questions. Practice. Question 1. As a senior analyst, you're asked to run a simple linear regression to predict the number of ice creams sold based on the temperature outside. Which variable is the dependent variable and which is the independent variable? Solution. The dependent variable is the one we aim to predict, the number of ice creams sold. The independent variable is the one used to explain it. Question 2. If the linear regression has a slope of 0.75 and an intercept of 120, how many ice creams will be sold when the temperature outside is 40 degrees Celsius? Solution. Substitute 40 into the model. Ice creams sold equals 120 plus 0.75 times 40, which equals 150. So the forecasted number of ice creams sold is 150. In the next class, we'll explore measures of goodness of fit.